Often, when computing expectations, we need to factor in information that we learn along the way. When we were computing probabilities, we introduced conditional probability, the idea that the probability of an event might change if I know that some other event has also happened or not happened. Because expectations rely on probability, this means that our expectations of events can also change when we know that some event has or has not happened. So here's a definition for you. If A is an event, then the expectation of X given A, or the conditional expectation, it's defined like this. We use the usual expectation formula where we sum over all the possible values that X can take, but instead of using just the regular probability mass function, we instead use a conditioned probability. So we say the probability that X has value equal to little x given that A occurs. We call this the expectation of big X given A, or alternatively, we also call it an example of a conditional expectation. So here's an example of when we might care about a conditional expectation. So in Texas Hold'em poker, here's how it works. You are dealt 2 cards for your hand and 5 cards are for the community, and they're available for all the players to use, including you. So in this picture I've taken here, so here's the 5 community cards, and then this player has 2 cards in their hand, and I'm intentionally not showing them to you yet. So what are the possibilities for the cards? There's 52 cards in a standard playing deck, and 4 of them are aces, and aces are especially good. So what's the expected number of aces that you would expect in the community cards? So you'll notice in this picture, here's 1 ace and here's another ace. So we got 2 aces in the community pool here. What's the expected number of aces that we would appear here if we were dealing cards at random? And then secondly, what if you actually have 2 aces in your hand already? How would that change the expectation? Okay, let's see if we can figure this out. So let x sub I, I'm going to use an indicator random variable here. Let x sub I be an indicator of the event that the ith community card is an ace. So I'm going to have here I going from 1 up to 5. Okay, so then the expected number of aces, I'm going to eventually use linearity of expectation, but what I'm going to start with is just noting that the expectation of a single xi, so we can think of xi as an indicator of the event that this specific card on the far left is an ace, that expectation is equal to the probability of that card being an ace, which is just the number of aces over the number in the deck. There are 4 aces, there are 52 cards in the decks, that's 1 divided by 13. So the expected number of community aces I'm going to get by adding all those up, which means I'm going to have the expected value. I'm going to let x here be the number of community aces. That's going to be the expectation of the sum from I equals 1 to 5 of all the xi's, which by linearity is equal to the sum from I equals 1 to 5 of all the expectations. There's 5 copies of 1 over 13 in that sum, and so my result is 5 divided by 13. So if I was not using any information about what's in the hand, my guess for the expected number of aces would be 5 over 13. But let's now consider the case where we actually know that two of the aces are already in our hands. If two of these aces are in our hand already, then there are just two left in the deck. So in this case, the expectation of, let's focus on one of the individual x sub i's, given the event 2 in hand, looks different. I need to consider the probability of that specific card being an ace, given that two of them are in my hand. Well, how many aces are left if two of them are in my hand? I started with 4, and so there's 2 remaining out of 50 other cards in the deck. So I need to subtract from both the numerator and the denominator here. If I have 52 cards, 2 of them are already in my hand. That means the other possibilities remaining, there's just 50 of them, which is 1 over 25. So the expected value of this random variable x, the number of aces in the community pool, given the event 2 aces in hand, well, if I do the same calculation I did before, I'm going to wind up multiplying this probability by 5, and so I'm going to get 5 times 1 over 25 equals 1/5. So by computing an expectation while factoring in all the information I have here, so I have new information that I have 2 aces in my hand. By factoring that information into my expectation calculation, I find that the answer has changed a lot, down from 5 over 13, which is well over a third, to 1/5, which is much, much less. So when I use conditional expectation calculations, I can calculate expectations in different scenarios using all the information I have in those scenarios in order to arrive at a result.